has a solubility of 43 grams KCl, 100 grams of water at 50 degrees C. So which of the following would be an unsaturated solution at 50 degrees C? So unsaturated means less than saturated. The solubility tells you the saturated solution. How much is the most that can possibly dissolve? So which of these is a number that is less than the most that can dissolve, less by ratio, and that is the first one. If you had 25 grams to 100 grams of water, you have less KCl in there than 43 grams at 100. So that's unsaturated. The second choice, 43 and 50 grams of water, that's twice as concentrated. So that would certainly be saturated. And then 50 and 100 would also be saturated. So if you tried to put 50 grams in 100 grams of water and the solubility is 43 grams, that means the extra 7 grams would just fall to the bottom and wouldn't actually dissolve. So that first one would be unsaturated. All right, some more solution chemistry. So potassium carbonate, we need a formula for that so we can get a molecular weight. So that's going to be K2CO3. And that weight, let's see, we've got 39 plus 39 plus 12 plus 16 plus 16 plus 16, 138. So that's 138 grams per mole. So if we want a 1 molar solution, that means 1 mole in 1 liter. If there's 138 grams in 1 mole, then that's the answer. 138 grams have to be added. That's 1 mole. We want 1 liter. So 1 mole per liter is 1 molar. And that's it. All right, which of the following would you expect to not pass through a semipermeable membrane? You tested some of these last week. The starch does not pass through that membrane. All that other stuff would. Now we tested water, chloride ions, and glucose. Urea is also a small molecule. That's how your kidneys work, is that the urea passes through the membrane into your urine. All right. Molarity of potassium hydroxide, again, we need moles per liter, so molarity is going to be moles per liter. We've got grams, we need to make that into moles. Potassium hydroxide is KOH, so that means that mass is 39 plus 17 is 56. Four grams, 56 grams per 1 mole. Tells us that we've got 0.071 moles. And that's in 2 liters of solution. 0.071 moles in 2 liters of solution. Is 0.036 molar. So the moles divided by the liters gives you the molarity. The last one, KF is a strong electrolyte and HF is a weak electrolyte. How is the solution of KF different from that of HF? So what's different in solution for KF versus HF? Yeah, so how's that? That's correct. So how does that manifest itself in solution? What does it mean to be a strong electrolyte?
It dissociates.
Right, it dissociates. So water, you're going to have individual ions in solution because the KF is broken apart in solution. Whereas HF, what's different there? Yeah, it mostly stays together. Only a little bit actually breaks apart. So there's some H plus and F minus ions in an HF solution, but it's mostly still whole HF molecules that have not broken apart. So that's the difference. So if you said something about that one is individual ions that have broken apart in solution, and the other is a covalent compound that mostly stays together in solution, that's what I was looking for on that one. All right, and that's quiz 5. So we're going to keep piling on the quizzes here. We'll have another one on Wednesday on acids bases, and then we'll have another one on next Monday on the nuclear chemistry that we talk about today. Actually, maybe. We'll see how much of it we get through tonight. If we get through it tonight, then yes. Otherwise, we'll probably put it off to Wednesday. But that's good, because that means, remember, we're only keeping 5 quizzes at the most. So if you've gotten 5 quizzes that have been good scores so far, you're set. If not, then you got more chances to replace ones from earlier that maybe didn't go so well or that you had to miss or something. Okay, so let's stop and take a break there. And we'll come back in about 15 minutes and talk about nuclear chemistry. All right, everybody excited and not tired? Yeah, everybody seems pretty alert. Happy to be here. No, that's all right. So right now we're going to go all the way back to chapter 5. We skipped over chapter 5 a while ago. We're going back. Go pick it up. There were a few extra points in the last exam. That was no, that doesn't count.
How about like easy or more accessible extra credit?
You can drop some quizzes. That's kind of like extra credit. You can replace an exam with the final. That's kind of like extra credit. No. Yeah, if you do well better on the final than one of your exams, I'll replace the exam with the final score. Some people have missed an exam, and so I usually just make that available to everybody. You know, if you have a bad exam, you can replace it with the final. So the problem with like traditional extra credit, like, you know, here, go do these problems, and then you get an extra 10 points or whatever. The problem with that is it's like, if the point of the grade of the class is to measure how well you've mastered the material. So if your mastery is at, let's say, a too low of a level, and then you just do some other mediocre work to kind of bump it up to a higher level, then the grade is not really an accurate measurement of how well you've mastered the material. It's more a measurement of like how much stuff you've done or something like that, which is different, which is okay if that's the way that you're measuring your class, but it's a different type of a measurement. So something like replacing an exam score with a final score, I think, is an appropriate measurement, because if you didn't learn something for the first exam, but then you did learn it by the end, great, you should get credit for that. So that still, to me, measures the mastery of the material in the class. So that's why I don't have any of that like other style of extra credit here. All right, so let's talk about nuclear chemistry. What do you think nuclear chemistry is? Any idea? Have you heard of nuclear reactions? What are nuclear reactions? Maybe not. What have you heard about nuclear reactions? Nothing. But you heard of them?
So like when you try to break atoms apart.
When you try to break atoms apart? Yeah. Yeah. That's an example of a nuclear reaction. But nuclear chemistry is actually broader than just that. We are going to talk about that. That's called fission. But it's a little broader than that, because it actually encompasses all the chemistry of the nucleus. That's where that nuclear comes from. And of course, the nucleus is the protons and neutrons. That's very different from all the chemistry we've been talking about so far. Because so far, we've been talking about the chemistry of the electrons pretty much exclusively. I mean, we kind of talked about protons and neutrons at first, but in terms of like what actually changes, how things interact with each other, that's all electrons. Ions is electrons, covalent bonds is electrons, chemical reactions, that's all electrons. So this is a totally different thing, which means this isn't going to play by any of the rules of the stuff that we've talked about before. These reactions are going to be completely different and totally do not fit any of the frameworks of the other stuff, which is why we kind of leave it till its own chapter later on, rather than throw it at the beginning where it might get a little bit confusing. So before we talk about the actual reactions themselves, we need to look at some other terms associated are often associated with nuclear chemistry. And the first is a pretty general term, radiation. Have you heard of radiation? What is radiation?
Does that have to do with like gamma waves or something?
Yeah, so gamma waves, that would be a type of radiation. What are some other types of radiation? Other examples? X-rays are a type of radiation. What else? The sun, sure, is emitting radiation. What kind of radiation is emitted by the sun? Ultraviolet, but also visible light, right? The radiation also, this is what's coming off of a light bulb. When light is transmitted from the light bulb across the room, that's a form of radiation. So radiation is very, very general. It's simply an emission of energy and or particles. So anything that comes off of something else and like shoots away is radiation. That doesn't mean that all radiation is dangerous, like visible light, for instance, or infrared light or whatever. Those kinds of things are certainly not harmful to us. In many cases, they're beneficial to us. We often associate the term radiation with a particular damaging type of radiation, so radiation that can damage us. And that is known, that's actually known by a special term, which is ionizing radiation. Ionizing radiation is the stuff you have to watch out for. Why do you think that is? What do you think ionizing radiation does? It changes something. What does it mean to ionize something? Yeah, to knock an electron off. So ionizing radiation is radiation with enough energy to remove electrons from atoms or molecules. So it can knock an electron off of something. And that's why we're often concerned about ionizing radiation. Because ionizing radiation can really mess with our molecules, our cells, our DNA, that kind of stuff. You knock an electron off of DNA, what happens often, or what can happen, is the DNA can kind of close back on itself, and the places where the electrons got knocked off can react with other parts of the DNA. When DNA is cross-linked like that, that's what causes cells to not replicate properly, and that can lead to things like cancer. So ionizing radiation can cause burns, it can damage tissue, it can have longer lasting effects like cancer, and that's why things, anything higher energy, ultraviolet or higher, is considered ionizing radiation. So that's why you don't want to get too much ultraviolet light from the sun. That's why you don't want to get too many X-rays, especially chest X-rays or head CT scans, that kind of stuff. And then the really high energy stuff like gamma rays, which come in from space, are especially high energy, but they also can really just pass right through your cells. So depending on the density, they can be more or less dangerous. All right, so we're going to talk about some forms of radiation. And the forms of radiation we're going to talk about are nuclear reactions that show something happening to the nucleus of an atom that then results in radiation, that results in something being emitted from that atom. In some cases, these are going to be particles that are emitted, and in some cases, they're going to be waves that are emitted, or light energy. In order to talk about that, we need to go way back to the beginning couple chapters when we looked at the symbols of atoms and how we drew the atoms. And if you remember, we had this, like, we take a symbol like iodine and we put a couple numbers by it. Do you remember a symbol like that? Those if we look at the periodic table now that we're a little more familiar with it, we can see what that means. So that 53 is the atomic number. That's the number of protons. And then the 131 tells us the atomic mass. Now that is not the same number that we see underneath the I on the periodic table, because those red numbers, remember, are averages of all the different isotopes, the different numbers of neutrons that atoms can have. When we deal with nuclear chemistry, we're usually dealing with a specific isotope, so a specific number of protons and neutrons in a specific atom or sample of atoms. So we're going to have these whole number atomic masses that are not usually going to be the same as what you see on the periodic table. So that is mass up there, the atomic mass, which is the protons and the neutrons added together. And this is the atomic number, which is just the number of protons. So what we'll see in these nuclear reactions is that these numbers will change as atoms come together or get broken apart or things shoot off of atoms, that kind of thing. Other ways that this will be written, sometimes that bottom number will be left off and we'll just have this. The reason for that is because that bottom number is really redundant. If an atom has 53 protons, we have to call it iodine. It has to be iodine. So we don't really need that number there. But as you'll see in these reactions, it can be helpful to put it there just for accounting purposes. And then if this is written in line, sometimes you'll see it like this, just iodine 131. That's how we would say that. So those all mean the same thing. Iodine 131 is an isotope of iodine. All right. Now let's look at some of the different forms of radiation that we can emit and the types of reactions that emit them. The first one is called an alpha particle. Now these things were discovered pretty early on in chemistry. Marie Curie famously discovered the radium as an early alpha particle emitter. And so these particles were kind of, nobody really knew what they were made out of. We didn't really have the tools to know what they were made out of, so they were given these names like alpha particle, X-ray, right? X-ray means like mysterious ray that we don't know about, basically. And so we know now that an alpha particle is actually a helium nucleus. That is, it's a nucleus, or it's a particle that has 2 protons and 2 neutrons. So it's written in one of 2 ways. It can be written as an alpha particle with just a symbol of alpha, and 2 protons and 2 neutrons makes atomic weight of 4, atomic mass of 4. But it's more commonly expressed as a helium nucleus, so we actually write He 2 and 4 as our alpha particle, because anything with 2 protons is really helium. So that's our helium nucleus. The type of reaction that causes an alpha particle to shoot off is called alpha decay. Let's look at an alpha decay reaction. Uranium-238, for instance, we're also going to be dealing with a lot of these big elements that we never see in other stuff, because the reason we don't see them in regular chemistry is because they're very radioactive, so we don't deal with them as much. But now that we are caring about that kind of thing, we'll start looking at the bottom of the periodic table a little bit more. So uranium-238 will decay, which means that it will break apart just on its own. These are just the nuclear forces that hold things together. They have a particular strength, and then sometimes stuff just comes off. That's the nature of what we call radioactivity. And so uranium-238 will emit an alpha particle. An alpha particle will shoot off of this atom of uranium-238. To complete the reaction then, all we have to do is figure out what the other remaining numbers are and then rename the element. So if we've lost 2 protons from 92, how many do we have left? 90. So we just write that this new particle is going to have 90 protons. And what's its atomic mass going to be? Yeah, 234. So what should we call this element? Is it still uranium? Right, it's now thorium because we have to look over for 90. We have 90 protons instead of 92. So it's no longer uranium, it's now thorium. And that's alpha decay. So all you have to know is that uranium-238 undergoes alpha decay, and you can write this whole reaction. So let's try another one. I'll write it in sentence form, and then you write it in reaction form. Americium-241 undergoes alpha decay. So see if you can write that reaction the same way. This is the reaction that happens inside smoke detectors. Alpha particles are emitted from an americium atom or some atoms. They go across to a target, and when smoke gets in the way, the alpha particles bounce off the smoke particles and don't make it to their target, and that's when the alarm sounds. So you first write the Americium-241, which has an atomic mass of 95. And then the alpha particle, and then whatever's left. Should something like that. Oops, I didn't save these notes. Hang on a second. All right, so that's all there is to alpha decay. Now, alpha particles are pretty big. They're pretty massive in terms of how how radiation goes. They're the bigger particles. Now, that means a couple things. One, it means that they don't get through stuff very well. And we'll see this in lab when we actually play with some, well, not play with some, carefully use some, I guess is probably a better way to put it, but it's kind of like playing with it. Some alpha emitters, we'll have some in lab, and you'll see that they're blocked by air molecules. An alpha particle can't really make it through air. It'll just hit, because it's so big, it'll just hit other air molecules and be blocked. So if you have a bunch of radioactive alpha emitter sitting on the floor over there and you're over here, it's not going to hurt you. It's not going to be a danger to you. Now that said, if an alpha emitter gets inside your body, it can cause some serious damage because now it doesn't have anything blocking it anymore, and it can just shoot these giant, from an atomic perspective, particles at your cells. And so a lot of dangerous stuff can happen from alpha emitters. That's often how things like, well, kind of these internal kind of cancers, lung cancers and things like that can sometimes be caused by things like radon getting into your lungs, the radioactive gas in your lungs and bombarding your lungs with alpha particles. Also, alpha particles are used in a therapeutic way. This iodine-131 that I saw up here, this is radioactive iodine, and that's actually used to treat thyroid conditions. The radioactive iodine goes to your thyroid. You need iodine for your thyroid. So the radioactive iodine, when you're treated with it, goes to your thyroid, and the alpha particles start knocking out part of your thyroid. So if you have hyperthyroidism, the alpha emitter can actually destroy some of your thyroid carefully and on purpose, so that you don't have that issue anymore. But if you do that kind of a treatment, or if you've seen that kind of treatment, you have to stay in the hospital for a while because all of your waste is radioactive at that time. And so they have to collect like all your pee and stuff, and you can't go anywhere until your radioactivity is back down to a suitable level or safe level. All right, so let's look at another, another type of decay, which is, I guess one was alpha particle, so two will be the beta particles. As with the alpha particle, the beta particle was originally named as just this mysterious thing that they just called beta because it was different from the alpha one. It was like the second particle they found. But now we know it's actually an electron. So beta decay is when atoms shoot off an electron. But the difference from the stuff we've already been talking about is the electron does not come from the electron cloud or on the nucleus. It actually comes from the nucleus. So the nucleus shoots out an electron. Are there electrons in the nucleus? No. So how does it shoot an electron out of the nucleus if there's no electrons in the nucleus? That is a great question. So let's answer it. No, what happens is something else is going to turn into an electron. So first, the way we draw a beta particle is we can do it kind of like the alpha particle. It has no mass or negligible mass and a charge of -1 because it's an electron. So instead of having a positive atomic number down at the bottom, it's actually a negative atomic number. And just like the beta particle, because it has two names, it's also sometimes written as an E, -1, 0, instead of a B, instead of a beta, -1, 0. That B with the long tail, that's a lowercase Greek letter beta. All right, let's look at some of these reactions, which are called beta decay. Now, before we look at the actual atoms, what happens in beta decay is a neutron decays. So a neutron, which is like this, hold on, there we go. Neutron turns into a proton and an electron. If you add up those numbers, you'll see it actually works out. The 1 plus -1 is 0, and then 1 plus 0 is 1. So a proton plus an electron is a neutron. Or in this case, a neutron breaks into a proton and an electron. So that's how the electron ends up in the nucleus. It comes out of a decay of a neutron. Which means that when we draw these reactions, or when we write these reactions of alpha decay or beta decay, we can still just follow the math and it works out just fine. Carbon 14 is a compound that decays by beta decay. So we're going to do it the same way we did the alpha decay. We're going to write the particle first and then figure out what else we have to put there to make everything balance out. So there's our beta particle, which means what has to be the top number in our other part of the product? What has to be up here? Yeah, 14, because it has to add to 0 to get to 14. And then what has to be on the bottom? Careful there. It's not 5. 7, right, because that's a -1 on the E. So this actually has to be a 7. Remember, in the course of this decay, we've actually gained an extra proton. What?
Oh, you're adding, sorry.
Yeah. So you're getting an extra proton, so that adds to -1 to get to 6. And what is that element called then? That's nitrogen. So that's how the beta decay works. And just as before, all we have to do is know what kind of decay it is and what the isotope is, and we can write the reaction. So if I said phosphorus 32 decays via beta decay, we could write that reaction. So go ahead and see if you can do that. Do something like that. So these reactions are kind of easy, right? All you have to do is put the particle in there, and then you can add up the numbers, and that's really all there is to it. All right, so let's look at the last one, which is really even easier because it's really just energy. The last one is what we call gamma rays. That's that Greek letter gamma. And instead of calling them particles, we call them rays, because this is actually just energy, just pure energy, just like light. It's just a type of light with really high energy, which means that the gamma particle, or the way we write an equation, is a little weird because it doesn't actually have any mass. It doesn't have any charge either. It's just light. So we just make a gamma with 0 and 0, and that's our gamma particle, our photon. This is a particle of light called. That's what a particle of light is called. So isotopes that undergo gamma emission do have to change in some way, but they don't actually emit any mass. So what they do is they change from a metastable state, meta means partially, to a stable or a more stable state. And the way we write that reaction looks like this. Instead of saying just 99, we say 99M. So this is technetium, which is a man-made element right in the middle of the periodic table. And metastable technetium decays into regular old technetium. Notice the numbers don't change. The M just goes away. And then we end up with a gamma ray that's emitted. So there's nothing tricky to do there at all. You just take away the M, and you put in the gamma ray, and that's all that happens. So what that tells us is that 99M means that isotope's at a little bit of a higher energy state. It drops down to a lower energy state and releases that energy via a gamma ray. This particular isotope, TC99M, is really, really important in nuclear medicine. In nuclear imaging, for instance, there are huge factories known as cyclotrons where they manufacture tons of this stuff. I mean, relatively speaking, it's not really that much, to do all kinds of imaging in the body. And you can read about some of that in the book. Let me grab a couple of these pictures. Might be too slow here. All right, while we're waiting for it, we'll look on. The gamma rays are just high energy light. And that means a couple things. On the one hand, they're not massive. They have no mass, which means that most gamma rays can pass directly through our cells because they can pass through molecules. Light rays can pass through the space between a nucleus and an electron. So just probability-wise, the chance that a gamma ray will knock an electron off of an atom is pretty low, unless you have a pretty high intensity, unless you really have a lot of gamma rays. And then it starts to become an issue because they do have enough energy to do that. Now, we're getting hit with gamma rays all the time that come from space. Because they can get through so much stuff, They can come from wherever in space, all the way through space, as long as they don't hit anything. You know, they keep going. They can make it all the way through our atmosphere, and they can hit us. And we start when we get in 2 weeks, I think we'll get out the Geiger counters and start measuring radioactivity. And you'll hear these kind of blips just from holding the thing up to the air, and that's from things like gamma rays that just come from space and hit us. And that's just happening. So don't let that freak you out, but that's happening. All right, let's see if we got our thing yet. Right, yeah, here we go. So here's a neat list of some medical applications of radioisotopes, of some of these different emitters. Generally, oh, and I was wrong about the iodine thing. I said that was an alpha emitter. It's a beta emitter. But generally, beta and gamma emitters that are used in nuclear medicine. Specifically, this one is used in all kinds of imaging of pretty much any kind of organ. So if you need some specialized imaging of any of your organs, chances are that's one that you'll encounter. It's pretty safe in the doses that it's used, and very effective. All right, so this thing's being super slow right now, so we'll just move on. A really important one that you should know about, Radon 220. Decays via alpha decay. So see if you can draw that equation. Write a nuclear equation for radon 220 decay. Remember, that's all the information you know, or you need to know. You can find the rest of it, 86, and then you draw an alpha particle, and then just figure out what else needs to be there.
So all of these units have helium in them?
That's the alpha particle. Yeah. Well, helium really is just 2 protons and 2 neutrons. We just call that helium. So that's what comes off of the nucleus. Yeah. Right. So what's important about this particular process? So this is pretty dangerous, and actually a lot of people are affected by it. You can have radon in your home. This is not. We think of radioactivity sometimes as this like weird, or as this very unnatural thing of nuclear bombs and things like that. But actually, this is all naturally occurring. And radon gas is one thing that is actually naturally occurring. And it's a heavy gas, right, very heavy, low on the periodic table, very dense, that is naturally occurring inside the Earth's crust. And depending on where your house is, or wherever you live is, you may have radon inside of it. And the radon will tend to go to the lowest part of your house. Now, the reason that's so bad is because of this, because it's an alpha emitter. That radon sitting in your house is not hurting you per se, but if you're inhaling it, because it's so heavy, it sits way down in your lungs and you don't exhale it. And so it sits down there and bombards your lungs with alpha particles, and destroying it causes lung cancer ultimately. So if you buy whenever you buy a new house, or if you haven't checked it in a while, you can buy these pretty cheap radon test kits to put in your basement. You let it sit there for a few days, and then you send it into a lab, and they check it, and they'll let you know if you have radon in the house or not. And I think all houses now are required to have it checked every so often, certainly anytime there's a sale. you transfer ownership of a house, because you have to know if the stuff's there. If it's there, it's not a big deal. You just put in this fan that kind of circulates air in your basement out, and that takes care of it. But it can be really dangerous if you don't know what's there. So if you, wherever you live, if you haven't checked for radon in a while, you may want to do that, or tell whoever owns the place or whatever that they should check for radon. All right. I want to look at one more type of reaction. I hope I can find the picture because it's really hard to draw otherwise. And that is this splitting of the atom, nuclear fission. Fission is just a word that means to break apart or to split. And this is really what people think of when they think of the word nuclear usually. That it has something to do with atoms breaking apart, nuclear bombs, nuclear power plants. This is what that's based off of. So rather than try to write it out, there's a very nice picture in your book, if I can actually get to it without crashing this whole thing. Oh yeah, so while we're waiting, okay, there it goes. I was gonna say that was a picture of a thyroid imaging. All right, here's our picture. This is what nuclear fission looks like. You've got kind of a picture of it first, and then what it looks like in a chemical equation, or a nuclear equation. A neutron hits a uranium nucleus. So this is not a natural process. You have to bombard uranium, specifically uranium-235, just this one isotope. You have to bombard that with neutrons. What happens is that neutron gets captured. It gets absorbed by the nucleus. And when it does that, it becomes very unstable. You can see that by these little lines floating around here. And that unstable nucleus breaks apart into two pieces. Turns into a krypton nucleus and a barium nucleus, and then it emits 3 more neutrons itself. That's kind of the key to this reaction. Most of these nuclear reactions, you'll notice, they go from a less stable nucleus to a more stable nucleus, and then kind of just stop there. Now, this might also be radioactive, is radioactive, and it will decay further, but not necessarily through the same mechanism. In this case, you bombard this with a neutron, and then it breaks apart, forming more neutrons. And that causes a chain reaction. So when you've broken that atom apart, not only have you released a tremendous amount of energy, but you've also produced more neutrons that can go hit other atoms and break those atoms apart. And so the thing is self-sustaining, and that's what we call a nuclear chain reaction. And a nuclear bomb that's simply allowed to go to release an incredible amount of energy. In a nuclear power plant, that chain reaction is controlled. And the neutrons are sort of, well, the neutrons are let go, but the uranium is more or less blocked, depending on how much energy you want to produce, by these things called control rods. So here's what the reaction looks like. And what you can see is those particle counts still add up. So we've got 92 on the bottom here. So that's 36 plus 56, that's 92. 236 on the top, that's 91. Plus 142 plus 3, because the 3 neutrons also are part of that mass. And that's what's known as nuclear fission. That energy released is the energy that we see. Yeah?
When you broke it into krypton, why just those two out of everything else?
Good question. That's just what happens.
Okay.
I mean, different atoms will break up into different nuclei. What's special about this is, like, you can bombard lots of stuff with neutrons and nothing happens. This particular isotope does this one particular thing, and that's what's so special about it. So when they talk about places like other countries trying to enrich uranium, have you heard that term, enrichment of uranium? And we're trying to prevent dictatorships from enriching uranium to get access to nuclear weapons. What that means is taking samples of uranium, which is mostly not uranium-235, it's mostly uranium-238, which is not radioactive. And there's a tiny bit of uranium-235 in there. And through a bunch of processes using fancy equipment and these centrifuges, you can carefully separate out the uranium-235. And that's how you isolate the fuel for a nuclear reaction, a nuclear fission reaction like this. So when they're talking about enriching uranium, they're talking about separating out that one special isotope that does this one crazy thing, because the other ones don't. So uranium's used in a lot of other stuff. Uranium's used in anything where you want like a really dense, heavy metal. There's uranium used in bullets to make extra dense, therefore damaging bullets that can get through stuff. That's known as depleted uranium. And that's uranium-238. So that's non-radioactive uranium, or very almost not radioactive uranium. And that has some other uses as well. The counterpart to nuclear fission, again here, is nuclear fusion. And this is what's happening in the sun. So the sun is doing this kind of a reaction. An isotope of hydrogen, hydrogen-3, is combining with another one. So two of the same atoms are combining to form a helium nucleus and a neutron and energy. Nuclear fusion, the fusing together of these things, actually creates far more energy than nuclear fission. The problem is it only happens at crazy, crazy temperatures. So for this to happen, you need to be at 100 million degrees C, which is pretty hot. So we can't really do, we've done nuclear fusion on Earth, but the energy that you have to put in to get up to 100 million degrees C makes it not really worth the energy that you get out. So the net energy is not really worthwhile. There are nuclear fusion bombs. They're called hydrogen bombs, and that's actually one of these nuclear bombs. A fission bomb is set off first to get to that 100 million degrees to start this thing going, and then release that energy. So that's kind of one of these great, what they call holy grails of science. If somebody could figure out a way to do fusion not at 100 million degrees. So far, it's not really working. So, but that could be something maybe you can discover, and if you could do that, that'd be great. That might be worth some extra credit.
Would that be great for the better or for the worse?
What?
Would that be great for the better or for the worse?
Yeah, that's a good question. Right. Kind of depends on who's using it and what they're doing with it, right? Yeah, just like anything else. All right. How are we doing? Okay, so the last two parts of this chapter are talking about measuring radiation and then talking about half-life, which is how we measure the rate of decay. So let's look at those. Now, there's two ways you can measure radiation. One is by measuring how much the actual radioactive stuff is breaking down. You know, like if we've got this radon that's that's undergoing alpha decay. All right, so how much alpha decay is coming off of it? And we have a couple of units for that. We're not going to spend too much time on these because these aren't really as important to us. But there's the Curie, CI. It looks like an A. After Marie Curie, who discovered radium. And there's the Becquerel, BQ, after Henri Becquerel, who discovered other type of radiation. And these both measure, they're different units, but they basically measure what we call disintegrations per second. So like how many times is an atom breaking down each second in a particular sample? These are going to be sample dependent. So like a big batch of some isotope might be like 80 curies worth of radiation. And then a smaller one would be 20 curies worth of radiation. So this isn't like an inherent measure of an atom. It's just like it's just like a measure of a sample. So if you, these measurements are important in things like nuclear medicine, because let's say you need a certain amount of radiation to knock out this tumor. So you need, I'm making up a number, but you need like 40 millicuries of radiation. So you figure out what isotope you're going to use and how much would give you 40 millicuries, and that's how much you use. But the other way to measure the radiation is by exposure. So the one side is like how much is it giving off, and the other side is exposure. And these are some units that you should know, because these have lots of important uses in like occupational health and safety, that kind of stuff. Two main units we're going to look at, the rad and the rem. Rad stands for radiation absorbed dose. And the definition of that is, let's say amount. The amount of radiation absorbed by 1 gram of stuff, whatever. So instead of measuring how much radiation is emitted by something, it's how much is absorbed. And that's a measure of exposure. Now, by 1 gram of stuff, that could be whatever. That could be body tissue. That could be a device. That could be something. It's just like a standard measure. But as you might imagine, that's not really a great measurement because different kinds of radiation are damaging in different ways. So to just say how much radiation in general is absorbed is not always useful. And that's why this other unit, a little star by it, is usually the one that we hear about, and that's the rem. And rem stands for radiation equivalent in humans. In other words, not just how much is absorbed by a gram of stuff, but how much would this affect a human if it were absorbed. And to calculate that, we take the rad and we multiply it by a particular factor depending on the type of radiation used. And you can look in the book about like the different factors. You don't have to know that, but basically like an alpha particle is a factor of 20 because it's 20 times more damaging to tissue than say a beta particle. So we would have this factor to then figure this out. And so when you hear about exposure limits, radiation exposure limits, that kind of thing, they're usually reported in rems and actually fractions of a rem. So the lethal dose of radiation, of ionizing radiation, is 500 rem. So you have 500 rems, you're exposed to 500 rems of radiation, and that will kill you. That's also 500,000 millirem. The reason I put that is because exposure limits and things like that are much smaller, so they're usually in millirem. Now the average for people, for like you and I living in a normal kind of area on Earth, an average area on Earth, is that we're exposed to about 360 millirem per year, on average. Now, that radiation comes from a few sources. As we talked about, it comes from space. It also comes from rocks, minerals, bricks. All minerals and things that come from the Earth's crust have some small amount of radioactive elements in them. Some radiation comes off of that and affects us. It also comes from getting X-rays. If you fly in a plane, that exposes you more to radiation because you're higher up in the atmosphere, so there's less atmosphere to absorb the radiation from space, from the sun, that kind of stuff. So that's kind of our average. Generally, we don't want to get more in our lifetime than about 25 rem, which is about 25,000 millirem. So that's how much you want to be exposed. You don't want to ever be exposed to more than that in a single dose. That's what we've kind of agreed upon is relatively safe, or about 5 rem per year. Okay, so any kind of occupational hazards, things like that, we'll say, make sure you don't have more than 5 rem per year. If you work with radioactive equipment, does anybody work with X-rays and stuff like that? Yeah. So do you wear like a badge of some sort that you get tested occasionally? No?
Some offices do
Okay.
have them, but ours, just because it's digital, so it has really low radiation. If it was not.
Yeah, so it might be they might keep track of it, but if you work with these kinds of instruments, or especially, like I used to work in lab with chemical X-rays, which are just X-rays that you shoot at chemicals. So they're super, super intense because they're not meant to go through people at all. They're just meant for analyzing chemicals. And we would always have to wear these rings, super fashionable, big plastic ring. And that we would send it in every month, and they would check to see if that ring had been exposed to X-rays. Because if it had, it meant there'd be something wrong in the instrument, and like you were at risk of exposure, and they'd let you know that you've been exposed to so much X-rays. Luckily that didn't happen, but that's usually how we monitor these kinds of things. People work with X-rays will wear some sort of device that measures the exposure to X-rays. It doesn't protect you from it, but it measures it. So that's the kind of exposures that you're limited to. That's also why, like if you have chest X-rays or CT scans, they'll keep careful records of that, and they'll try not to exceed a certain number of that per year, so that you keep under these exposure limits. Any questions about that exposure? You can find some more information about that in the book as well. All right, last thing we're going to talk about is half-life. Anybody know what half-life is? It's used in a few different situations. Half-life of a drug is one of them. So what does that mean? Or what's it a measure of?
Like, what's the potency of it?
Kind of. It's actually a measure of how long the drug stays in your system.
Oh, right. So
Yeah. Yeah. So like a longer half-life means that it's going to stay in your system longer. That's basically what half-life is. Like, how long does this thing last? Specifically, how long does it take for half of it to decay? So the half-life is the time. Half-life is a measure of time. Time it takes for half of a substance to decay. Now, when we talk about medicine, when we say decay, we really mean metabolize, like your body breaks it down and gets rid of it. When we talk about radioactive substances, we're talking about the radioactive decay. So you have the sample of radon, it's emitting these alpha particles. How long does it take for half of that to be gone? Well, not really gone, but become something else. So how long till half of it becomes something else? So let's say you started with 10 grams of some substance. And let's say you have a half-life. Let's use a real example. Let's say we're going to use this iridium-192 isotope. And this is a radioactive isotope that decays, and its half-life is 74 days. Another way that half-life is written is a T with a little 1/2 below it. So that means half-life, time it takes for half of it to be gone. So if the half-life of iridium-192 is 74 days, and we've got 10 grams of it, how long will it take until we have 5 grams of it? 74 days, right? Because that's the time it takes until there's half of it. And that sounds simple, but that's really how you do these kinds of problems. You just count how many half-lives it takes to get to a certain amount. So let's say I asked you, how long would it take until there are 1.25 grams left? So we got 10 grams, half-life is 74 days. How long would it take until there are 1.25 grams left? So what we have to do is we have to keep splitting that 10 in half until we get to 1.25, figure out how many half-lives that is, and if each half-life is 74 days, we know how long. So I usually just draw like a little map with arrows. So 10 grams, 1 half-life gets us to 5 grams. Another half-life gets us to 2.5 grams. And another half-life gets us to 1.25 grams. So it took us three half-lives to get from 10 to 1.25. You see that? How that works? We cut it in half 3 times. This is a little bit weird because we're not used to this kind of a problem. So one mistake that I'll see a lot in these types of problems is people will like want to divide. They'll say, oh, we start with 10 grams, we end with 1.25, so 10 divided by 1.25 is whatever, and that's the answer. But that's not how it works here. We have to cut in half a certain number of times. Now, if you're more math-oriented, there are formulas for this. It has to do with the power of 2. We're not really going to get into that in this class, but if that's something you want to have fun with, go for it. I can help you with that if you want. I like this way of just kind of counting it out. So you've got 3 half-lives. How many actual days is that? 222 days. So you took the 3 half-lives. Each one is 74. So 74 days, 74 days, 74 days. That's 222 days. Each half-life then, 74 days, 74 days, 74 days. So after that certain amount of time, we have a certain amount left. Half-life is really important in things like nuclear medicine because you want to choose your isotope. Generally, you want something that has a pretty short half-life. Not so short that it just like disappears immediately, but short enough that it's going to decay in a reasonable amount of time. So like that metastable technetium, that TC99M, has a half-life of like 6 hours. So they can do the imaging they want, and then in 6 hours or so, it's gone. It's all decayed, and so you're not radioactive anymore. So that's one reason that that's a useful isotope in medicine. You can also think about half-life in terms of radioactivity, the amount of radioactivity, because as the sample decays, the radioactivity will be cut in half also, just like the amount. So we might say that, let's say the same sample of iridium let's say we have a sample that is 8 times 10 to the 4th becquerels worth of radiation. So that's some amount of radiation. Remember, that was a measure of like how much actual stuff we have that's disintegrating. Let's say, and so then we might ask, what is the radioactivity after 74 days? Assuming we've got the same stuff. After 74 days is 1 half-life, right? So what should the radioactivity be after 74 days? Yeah, right, half. So 4 times 10 to the 4th instead of 8. We cut it in half. Another 74 days, cut it in half again. Another 74 days, cut it in half again. If you want to know how much is left in between, like in that after, let's say, 50 days, that's when you need the equation. That's when you need to actually model this thing. It's something called exponential decay. So you need this equation that has a 2 to the n power and all this stuff. And you can do that, and that's fine. We're not going to do that in this class, so I won't entertain you with such things. But this is how half-life works. All right. Let's take a look at a question from the book, and we'll finish up there. We can actually get it loaded up. It went a little faster last time, I think. While we're looking at this, so here's why that division thing doesn't work. If you cut in half each time, you end up with this kind of a curve. So it's not linear decay. It's not like you're losing a set amount each time. You're cutting in half each time. So it looks a little bit different. Okay, looking for one. A little bit. Okay, let's take a look at this question. One thing that these isotopes are used for is something called carbon dating. You can take, we will assimilate new carbon until we die, and then the carbon kind of just sits there. So you can, based on radiocarbon dating, you can figure out how much carbon-14 is in an old, dead, living thing, plant or whatever. And depending on how much carbon-14 is there in relation to carbon-12 and carbon-13, which are the more common non-radioactive isotopes of carbon, you can figure out how old it is. So in this case, let's say we obtain a sample from a prehistoric animal, and we figure out that the sample shows, there's a lot of information there. The sample shows that 4 half-lives have passed since that animal died. So the carbon-14 has decayed in its cells so that 4 half-lives have passed. So then if each half-life is 5,730 years, how much total time has elapsed since the animal died? Well, we can calculate that. So each half-life is 5,730 years. So 4 half-lives, thanks, is going to be 4 times that. So we can say that that animal died about that long ago. Because of the half-life of carbon-14, that's why carbon dating is only really useful with really old stuff. Because anything that's less than 5,700 years old, you can't really, or that died less than 5,700 years ago, you can't really use carbon dating to figure out, because there's still just as much left as with us. That's not exactly true. You can get a little closer than that, but it's mostly for very, very old things, but it would be many, many half-lives that you can use to figure out. And there's other isotopes as well that show the same effect, and we can use radioisotope dating and things other than carbon as well. Well, by we, I mean like people. I don't know how to do that.
So this is for like dinosaurs?
Yeah. That's how we know how old dinosaurs and stuff are. All right. Questions? Concerns? Yeah.
I have just, it's like a goofy question, but
Okay.
the whole Chernobyl thing, you said that, what type of radiation is that? Is it uranium or something like that? Reason why it has such a long half-life before people could still.
Yeah. I don't know the exact chemistry of all that, but generally those nuclear accidents, right, you're producing nuclear, so you've got all this nuclear active material. It melts down and it decays into other radioactive stuff that's then emitting all kinds of other radiation. And that's actually mostly gamma radiation that's causing that problem. And the reason it sticks around so long is because, first, because of half-life, because the stuff there, it emits when it emits. You can't make it go faster. You know, you can't like get rid of it faster. Those things, if it's a half-life of 1,000 years, it's a half-life of 1,000 years. You can't make it go away faster. You can like sequester it and put it in a vault with materials that it can't get through, but you can't make it decay any faster than it decays. So nuclear, that's one of the problem with nuclear waste, is that the waste from a nuclear power plant, for instance, is still radioactive. And so has to be kept safe and away from people until it's totally decayed, which in some cases could be a really, really, really long time. So that's why it's still around, because it'll keep decaying until it gets to a non-radioactive like product, and then it stops, but we can't make it get there any faster.
And the reason why we use it is it's more powerful than other using power, like electricity is
Yes.
way more powerful.
Yes, so nuclear power, the power density, and this is in the book, but let's, here.
Oh, okay, it's in the book, I didn't see it. But
You can look at it, I don't know if it has that number in there. Yeah, so like plutonium-239 is a radioactive byproduct with a half-life of 24,000 years. So like you have to put it somewhere basically where it's going to be stuck there forever. But it's a relatively small amount of material. Like a tiny amount of uranium is going to have enough energy to like, I mean, I'm making this up, but it's like almost an unimaginable amount of energy in like this much stuff. So you have a tiny, tiny amount of fuel. It's completely, well, it doesn't have any greenhouse gas type byproducts. So you're not producing carbon dioxide or anything like that because you're not burning anything. It's clean, there's no soot, there's no pollutants, nothing like that. All you have to do is figure out a way to store that bit of waste that's going to be radioactive for thousands of years. So that's why it's been a trade-off, and it's why like we get a lot of our energy from nuclear power, because in many cases it could be a really good trade-off. Yeah, you have some nuclear waste to deal with, but while you're actually producing the energy, there's really no byproducts other than that waste. There's no pollution, there's no carbon dioxide, greenhouse gases, that kind of stuff. So that's how we use it. And a lot of people think if we ever want to get away from fossil fuels, that nuclear power is one of our only real viable options, at least until things like solar power get more developed and more technologically feasible. Oh yeah. Good question. Other questions? All right. So we'll have lab on Wednesday, acids and bases. There's only 3 labs left, and one of them we actually miss because of the Thanksgiving holiday. We don't have that Wednesday, so we will miss that lab, but we'll do it. We'll probably do it on the last day at checkout as part of the checkout. So it's the nuclear lab, so it's kind of fun, but it's also kind of tedious, so we'll just kind of do it together as a class because there's not that many things. But yeah, just 3 labs left. So Wednesday, we'll have a quiz on Monday on the nuclear stuff. So it'll be like writing nuclear reactions and half-life calculations. So you can practice that in some of the book problems. And then next week, we'll get into organic chemistry for the rest of the semester.
Are we having that quiz on Wednesday?
Yes. Oh, that's right. Thanks for reminding me. Yes, Wednesday, quiz on acids and bases right before we start the lab.